Hello everyone, I'm Vipin Yadav from Virginia Tech. I'm a PhD student and I'm going to be talking about observation of low spin cone angle in cobalt palladium multilayers at low laser fluence using ultrafast spectroscopy. This research is based upon the work supported by the Air Force Office of Scientific Research. So to give you guys a brief motivation about my research. So as the technology advances, we are looking for faster and larger storage devices, and that leads to us that leads us to do research on the devices which where we can store the data more efficiently. So for example, Intel's meso devices, which looks beyond CMOS devices. This meso device, as the name suggests, magnetoelectron spin orbit transistors. It is based on spin magnetism instead of charge, and Intel claims that it can operate at just very low voltage of about 100 millivolt, and they claims that it's 10 to 30 times more efficient than traditional CMOS transistors. So to give you a brief idea about these devices, it consists of four components. First, a charge interconnect, which converts the voltage or current into charge using ferroelectric capacitors. The second component is uses magnetoelectric effect, which converts the charge into magnetism using multiferroic materials. And the third component is spin orbit effect, which converts this magnetism back to charge again using spin orbit coupling sets. And the fourth component is again a charge interconnect, which converts this charge into current, and our output is in current. So my goal is to study the spin orbit coupling stacks using optical spectroscopy. Now, why optical spectroscopy? Because as we all know, it's an extremely fast method, as because a laser pulse could be as short as 5 to seconds, and even now it's about 8 to seconds. So that brings us to our sample of interest here. And I'm working with cobalt palladium thin films, which is grown by our collaborator from Tokyo University. So we have 5 layers of palladium and cobalt alternating. Mm, For the scope of our study, we have divided our sample in two categories. I'm calling the first category as NN series, where I have kept the palladium thickness same as 0.50 nanometer and varying the cobalt thickness. In our second categories, it's KY series, where we are keeping the cobalt thickness same and changing the palladium thickness to study the spin dynamic, how palladium and cobalt thickness introduce different properties in spin dynamics of these materials. Here, NN and KY are just the initials of our sample grower. So we are using pump probe time results spectroscopy using an ultra-fast titanium sapphire Morlock laser, whose its pulse duration is about 100 femtoseconds and repetition rate of 76 megahertz. So by changing the pump and probe pulse using a mirror stage, we can delay them from each other, and by controlling this delay, we can have time resolved measurements. And the new thing about our study is that the fluence regime we are working with is about 1,000 times lower than previously studies. It's about like the lower region of microjoule per centimeter square. So to give you a brief idea of the TR-MOC results we got from our samples, I have put 3 series here. The first one, SO series, is from one of our previous students from our group who graduated, and he worked with varying both cobalt and palladium thickness. The graphs shown here shows TR-MOC signal response versus time delay with a function of fluence. And you can see the fluence varying from about less than like about from 0.5 microjoule to about 6 microjoule per centimeter square, and we can see clear oscillation and how this oscillations varies with decreasing fluence. I'll come back to these results at the end again and can discuss it more qualitatively. We also did magnetic field dependence, where we see that increasing magnetic fields increase in precession frequency. And using LLG equation, we can relate this frequency with the external field. We also did pump polarization dependence, where we used right circularly polarized light, left circularly polarized, and linearly polarized light as a pump beam, and we saw no difference in TR Mach signal. So the phenomena behind this precession of magnetization, what we concluded so far is when an external pump pulse hits the sample, it changes its magnetocrystalline anisotropy very rapidly, which induces a torque at the interface. This torque is also known as anisotropy-induced torque, and this torque is transferred to the adjacent ferroelectric layer, which is cobalt, and the whole system gets now knocked out of its equilibrium position. And as it starts getting back to its equilibrium position in the direction of effective field, the spin precesses. This effective field can be defined as the sum of demagnetization, anisotropy, and external field. And using the LLG equation, we can map out this precession. So our ultimate goal is to find the spin cone angle in real space. So for all optical magnetization switching, we require at least 90 degrees of spin cone angle. So to find the spin cone angle, Yamamoto et al. In 2013 connected this change in magnetization with the amplitude, the curve rotation, and the real cone angle. And so using this equation, we can find del theta, which is our spin cone angle in real space. And we can calculate the theta curve from the magneto-optical signals obtained from these different samples using curve microscopy. So back to the results and comparison here. So there's a lot going on in this slide, and so I'll be brief about it. So using the TR Mach signal, we have calculated amplitude, frequency, precession lifetime, Gilbert damping coefficient, saturation field, effective field, and equilibrium angle. Once we have this factor, we can also calculate the real spin cone angle. So to notice here, for SO series, we can see that different cobalt thickness provides different amplitude, and same in NN series. As the cobalt thickness varies, we are seeing different amplitude. And for KY series, where the cobalt thickness is same, for all three of the sample, we have about 16 microrad of amplitude. So that proves that the whole precession is coming from the cobalt thickness only, and that's the only cobalt thickness matters with the amplitude of the precession. However, the palladium thickness provides the spin pumping. So, and the another interesting part is comparing to the SO series and the KY series, where the cobalt thickness is about the same, 0.78 nanometer, we see a huge difference between the amplitudes of oscillations going from about 0.2 to 17 microradian per second, which leads us to a larger spin cone angle for KY series, about 45 degree. So we talked to our collaborator like, okay, the thickness is same, the cobalt thickness for both of these samples, but why are we seeing this huge difference among the amplitude of oscillations? So after talking to them, they provide the information about how the samples were grown, and they implied that the KY series were grown in a better experimental conditions, meaning that the interfacial smoothness was better for KY series. And the another explanation can be understood using the magnetization hysteresis curve by studying their paramagnetic anisotropy. And So this brings to the conclusion and future prospect. So we saw that decreasing cobalt thickness leads to decrease in oscillation amplitude. We saw an increase in oscillation frequency and an increase in Gilbert damping coefficient. While decreasing palladium thickness, we observed no change in amplitude, it's very slight change in frequency, and the effective Gilbert damping coefficient was almost same. And we saw a real spin cone angle of about 45 degree, by far the largest spin cone angle observed at this lower fluence regime. Our future prospect could be studying the high quality cobalt palladium multilayers, and look, we can also look at a different fluence regime between 50 to 100 microjoule per centimeter squares. And that concludes my presentation. Thank you. And let me know if you have any questions.
Thank you for the nice talk. If anyone has any questions, please put them in the chat or raise your hand. We have one question from Hilby. He says, how do you determine what thickness to keep constant? E.g., for the NN samples, the palladium thickness is kept at 0.5 nanometers, while for the KY samples, the cobalt thickness is kept at 0.78 nanometers.
These were provided by our collaborator. They used dam measurements to find the thickness of these samples.
We have one more question from Olivia. It says, how have you done diffraction on your samples to better characterize their film quality?
We have not, but that could be another future aspect of this work. Thank you for that.
I have one quick question is, your TR MoCA experiment, is it sensitive to all of the multi-layers, or is it more so just sensitive to the top layer in the stack?
So the laser has some penetration depth. So there are only like few amount of layer we can use, but the 5 layers here like are the optimized number so far in this research study, where we can see the whole contribution comes from all the layers.
Okay, let's thank our speaker one more time.